You still seeing my screen? Or did it go away?
I can see it.
Okay. It took the green bar off. So I wasn't sure. So welcome everybody to Chem 140, which is organic and biochemistry. My name is Isaac Roussel. This is my third semester teaching this course. Everybody calls me Izzy, so you're welcome to call me Izzy, Isaac, whatever you want. We're going to talk a little bit about me and then talk about the course a little bit. And I'll be clicking, letting people in. Okay, yeah, it says it's recording. All right. So a little bit about me and my background. I have a bachelor's of science in chemistry from the University of Michigan. I have a master's from Eastern University. I worked for about 10 years in the chemistry field and moved into IT, where I've been for the last 25 years. I am a certified user experience designer. I've worked as a programmer, business analyst, and a manager of a software development team. I'm currently working at the University of Michigan Medical School in their IT group supporting the medical school initiatives. I have 3 jobs because I'm insane. And so my second job is I am a senior rabbi of a local synagogue. And on top of that, I teach part-time chemistry at Washtenaw Community College, which we're doing tonight. I have a wife and 3 grown kids, all that are out of the house. But now I've got 1 grown kid back because my mom moved in with me last summer. I think I had some slides here. So there's me being a rabbi. That's back when I had brown hair. It wasn't all gray. I'm a video gamer. This is actually a screenshot of me playing in Halo 3. I love playing video games all the time. I started with Pong. So this goes way back. And I also enjoy reading fantasy genre, and I'm a big Dungeons and Dragons player. So you guys figure out I'm a nerd here pretty quick. Last year I got into bonsai. This is Toranaga, my one and only bonsai tree. But I was born with a black thumb, so the fact that Toranaga is now 1.5 years old is really amazing. He's been doing pretty good. Matter of fact, I probably need to trim him some here. I've just been afraid to. And my recent obsession has been kilts. So here I am in one of my kilts from last fall. And I've been working from home with COVID for the last 2 years. And the University of Michigan told their IT people, you're never coming back. So I'm working from home forever. And so I was like, hey, if I'm working from home, I'm going to wear something comfortable. And let me tell you, kilts are very comfortable. Anyway, so that's a little bit about me. Syllabus review. We have 6 tests in this course. There are no quizzes or homework. I give you some problems to work at out of the book from the end of each chapter, but it's not graded. It's just merely for you to test your knowledge and prepare for the exam. I am introducing this semester. I've not done this before. I found this program called Quiziz, I guess is how you pronounce it. But it's basically, if you guys have played Jackbox games, it's kind of very similar to that. So each week, I'm going to start the class off with you guys reviewing the previous week's material with some questions. Again, it's not graded, but it's just a way that we can review the material and talk about it. 75% of this class is based on lecture and 25% is based on lab. I don't really know what goes on in the lab. They're not in sync. So I got an email earlier today, somebody saying that the lab schedule was an old one. Asma, who's teaching the lab, will need to update that. I don't really know anything about what even happens in the lab, what material are covering or anything. So it'll be up to her to do that and up to her to grade your labs. So she'll be covering that more with you. What night is your lab? Thursday night, is that right? Tuesdays and Thursdays?
Yes.
Okay. Class participation can affect things. So I am not one of these professors that requires your video camera to be on, but if it is on and if you're asking questions and interacting with me, that tells me that you're participating and engaging in the material. And at the end of the semester, if you're on the edge, I can weigh in on that, and it might knock your grade up to the next higher level if you do participate in class. So I encourage you to come to class and participate. And I'd like at least a few people to have their cameras on if you're willing, just so I'm not talking to a wall all the time. But that's up to you. The schedule that I put together is tentative. It may change. Let me get this person in here. Some lab material may not be covered in lecture. Like I said, I don't really know what even happens in there. And so you're not tested on it. If it's not covered in the lecture, then it won't be on the test. So you don't have to worry about that. The slide decks are up already, but I probably will be modifying them as the weeks go by. These are my slide decks from previous semesters, but I'm always tweaking them and changing them. And I will be recording each week and posting that up on YouTube, and I will have the link in once I post the first one tomorrow. I will put the link in there so that you guys can get to it and be able to watch and review them if you'd like. I sent out an email about a syllabus survey. This is your first assignment. It's not graded, but I need you to do it. This is how we validate attendance. And it also affects financial aid in some regards. I'm not privy to all the details of that, but apparently it does affect things. So need you to go in and fill that out. All you're saying is yes or no, I read the survey. That's all it is. New material builds on previous material. So you need to keep up. This is really important. The first 6 chapters we will be taking pretty slowly. And these cover organic chemistry, and then chapters 7 through 15, we get into the biochem. These later chapters are shorter. We won't go into the biochem as in depth as we do the organic chemistry, but the biochem does build off of the organic chemistry. So if you get behind and then you get to the more difficult biochemistry stuff, you're gonna be struggling. So best to keep up. Let me see here, gotta find my way around. How do I minimize this? In the syllabus, I probably have to escape, right? Okay, in the syllabus, I put together a calendar. Again, this is tentative, but I think we should be able to stick to it pretty good. Tonight, we will cover chapter 1, next week 2, And then next weekend, you will be taking the first exam. All the exams are multiple choice, true or false, matching, ordering things. There's no fill in the blank. There's no math that you're doing for this course at all. And as a matter of fact, the exams grade automatically, which I love. I don't have to grade exams unless there's an issue. So I believe I have the exam set up so that you will get feedback right away. You can review that. If you think that you got a question wrong and it shouldn't have been, just email me. We'll take a look at it. These exams have been through 2 semesters, so I think I've worked all bugs out of them. But who knows, there might be a bug in there. And if you got one right, you think you should have got it wrong, you can always email me about that too. But nobody's ever done that before. So that first weekend will be the first exam. And then in February, we will do chapter 3, chapter 4, and then that following weekend will be the second exam. Then we'll do 5 and 6, and the very end of February will be your third exam. So let me say this too, because I didn't, is you have all weekend to take the exam. It will kick off Saturday morning and run till midnight Sunday night. But once you start it, you've got 90 minutes to do the test. And that's really plenty of time. I think most people get nowhere near the full 90 minutes on my exams. And so I had a calculus professor in undergrad who had the philosophy that no one should ever finish a test in the time allotted. And so he gave us these massive tests. I mean, they were literally like that thick. And he knew you weren't going to be able to complete them all. It was a pretty wild class. He was a kooky dude. But anyway, so you'll have all weekend to take the exam, but once you start it, you've got 90 minutes to complete it. And then, like I said, you should get your score right away. March, then, we will move into biochemistry. Chapter 7, then we have spring break. So I blocked that all off here. Then we'll do chapter 8 on the 15th, the Ides of March. And then exam 4 will cover chapter 7 and 8 with you there. And then 9 and 10 are shorter chapters, so we'll do those together in one night. Then chapter 11, and then your exam 5 will be the first weekend of April on chapters 9 through 11. And then we will do chapter 12, chapter 13, 14, and 15. And then the very last night of class, we will have the 6th and final exam. The last exam, I should say. There's no final exam in this course. So you're never going to get tested on alcohols once you have your test on alcohols. Now, concepts might roll forward, but there is no final comprehensive exam. They've talked about changing that, but hasn't changed yet. So, and then the grades will come out shortly thereafter. And that's it. Any questions about any of that or comments, concerns, anything? Oh, I got chat. This is the one thing I do not like about Zoom is it won't make a sound when people chat. Oh, it's nice to meet you. Awesome that you like D&D. Yeah, I'm running a campaign I just started. And I just discovered a program that you can build 3D maps with miniatures. It's pretty cool and very addicting. I've been spending way too much time building maps out. The labs are all in person. Unlike previous semesters, because of COVID, we were doing them online. I taught a Chem 122 lab last year online, which was very weird doing a lab online, but now they're back in person. So you do need to go up to campus Thursday night to do your lab. Yes, everything is on Blackboard. You'll be able to do your exam there, and see your grades. You can message me through there, or you can just email me directly, either one. So everything's on Blackboard for you. The syllabus is up there. The survey that you need to do is up there as well. So everything runs through Blackboard. Yeah, it's called TaleSpire, T-A-L-E, and it's pretty nifty, pretty cool. I don't think I have it running right now because it is a resource hog, but check it out on YouTube. It's pretty cool. Any other questions, comments, or anything? Somebody's got their hand up. Sierra?
Yeah, can you hear me? I don't know if I think I took my mute off.
Yep, I can hear you.
Okay, if there is a day that we know that we're gonna miss, is there are we gonna any repercussions to that if we miss a lecture one day? Are we gonna be able to get the notes that we miss?
Well, like I said, I'm recording every session, so you'll have
Okay.
that. You can watch it later.
Okay.
Alyssa just asked, will exams have any content from the book? No. If I don't talk about it, you won't be tested on it. So, and there's actually some stuff I talk about you won't be tested on either. So I'm not going to ask you what program is really cool for building D&D maps. So you don't have to worry about that. So yeah, I'm not doing all the material in every single chapter. If it's not in the lecture. So really the book, let me go back to my slides. I have to do slideshow again. Okay. The book is really more of a resource. I might have that on the next slide here. Yeah. So you can get this book physical, or you can get an online version of it. It's not required, but my problems all come from there. So, you know, if you want to be able to do those to check things out. I always tell my classes, when I took chemistry back in the early 80s, I had nothing but a book. You guys got so much stuff at your fingertips. If you're having trouble understanding something and you watch my lecture and you read the book and you're still confused, get on YouTube, man. I mean, there's a lot of stuff on there. Khan Academy is great for teaching stuff. There's a guy called the Organic Chemistry Tutor. He actually covers a lot of material other than just organic. But he does a really nice job as well. And then there's another one that's, I think this was Ninja Nerd, was more biochem, but they all do really great stuff. And that's just ones that I found and liked. There's tons of stuff out there. And going to websites and that kind of thing as well. You guys have a lot of resources to work on things. And I'm, of course, in the resource as well. I will try to respond within 24 hours to your emails if you send me an email. I do not email Friday afternoons through Saturday night because that's the Sabbath. So if you send me one there, it could be a little bit longer. Sometimes I get on after dark Saturday night and look at things. Sometimes I may not look at it until Sunday, depending on what's going on. And I'm typically available Sunday mornings if you really got to talk about something or something like that as well. Going back a slide. I put together this, again, very tentative outline of how our classes will go. So 6 to 6:30 will be a review of the previous week's material. Like I said, we're doing that quizzes thing. And then 6:30 to about 6:55 will be new material. We'll take a break. Then we'll do another section of new material. And then we're going to have some time where you guys can maybe work in teams on some, we're not going to do this tonight, but where you guys can maybe work on some problems together and present it to the class, or something like that. Or it might just end up being time for you to work on some problems, and then I'm here to answer questions if you have them. We'll see. And then another break, and then finally we'll have a Q&A time and wrap up. I'm also a huge history nerd, and I was talking to my daughters about this fact a couple of weeks ago, and they said, hey, you could put in some stuff about history. So you guys have had Chem, 101 or 105 or something, right? You learn about Avogadro's number and Planck's constant and all these kinds of things, but who are these guys and where do they come from, right? These are people. So I'm going to throw in some history highlights in this class this term as well. This is kind of new. You will not be tested on this material, but just throwing a little bit extra flavor in there to kind of get a feel for like how things developed in the particular topic, or who was involved, or that kind of thing. Somebody else has a question. I noticed the lab is out of date. Yes, that's something that Ozma will have to deal with. I did send her an email and said, take a look at it, but apparently she hasn't done it yet. So if it's not updated by Thursday, I'd go ahead and reach out to her. I'll probably ship her an email too, but you might want to reach out to her to find out what's going on. Okay. How about you guys? Why are you taking this course? I know a lot of people are going into physical therapy, nursing. I've had some people taking this because they wanted to go into the dental school. Tell me a little bit about y'all. You can speak it out or you can type if you don't want to speak.
This is my last class. I'm going to try to apply for PA school through Eastern.
PA being?
Physician assistant.
Oh, okay. Are you a nurse now?
No, I'm actually working radiology. I'm a vascular interventional radiology. So that's what I'm doing now. I just want to be able to do a little bit more with my hands, do my own procedures, that kind of thing.
That's cool. So as a PA, I mean, the only PAs I'm used to or familiar with is like at a doctor's office. Are you going to be like that, or are you going to be doing more just?
I prefer more like in like an outpatient surgical center, that kind of thing. I'm more procedure oriented, but I mean, I certainly am open to anything. But I'm more procedure geared as of right now.
Alrighty, cool. I see.
I'm taking. Oh,
go ahead.
I'm taking this course. I actually just received news that I got accepted to the dental hygiene program at U of M. So I start May 3rd.
Sweet.
Yeah. So this is my last class I have to finish up, and some. I'm taking cytology this semester, and then I start at U of M. So I'm thrilled.
Wow, mazel tov.
Thank you.
Somebody else is working towards their nursing degree, a master's at U of M. What's the master's then, Erin?
Oh, I'm also speaking of somebody else it's their last class for PA school. Also my last class for PA school. So I feel you.
Okay. Yeah, more nursing people. Freshman at U of M meeting the class for nursing. You're all making me scared when you say this is my last class, so do well. I don't think my class is tough. I don't see myself as an adversary to students. I'm here to help you. and I will do anything I can to help you succeed. So everybody says PA school, I think Pennsylvania, but physician's assistant. Cool, that's awesome. Okay. Oh, here's my joke of the day. This is caution, wet floor, and there's H2O molecules all over the floor. I had a different joke in here, but I realized we hadn't covered that material yet, so I'll save it for when we get to that chapter. But I figured you guys knew what H2O was. All righty, anything else before we start with the first slug of material then? What time is it? 6:30, look at that, pretty good. Okay, so we'll start our next slug with this. So tonight, chapter 1, we're going to talk about saturated alkanes. And there's different branches of chemistry. There's organic chemistry, which we will be, of course, spending quite a bit of time on in this class. Inorganic chemistry, which is what you largely had in your Chem 105 or equivalent that you've taken previously. Biochemistry is the chemistry of the body. Oh, and let me tell you guys this. So a year ago, they said, hey, Izzy, we want you to teach this organic biochemistry class. And I said, that's great, but I've never had biochemistry. And they're like, oh, you'll be fine. So last 2 semesters ago, I was literally teaching myself the biochemistry material as I was going in the class. And I found it absolutely fascinating. My background was all inorganic and analytical chemistry. So analytical chemistry is measuring stuff. And that's been really my main focus. I worked in a commercial laboratory for the first 14 years of my career, first as a chemist and then later in IT. So we were analyzing stuff, and so that was really my focus. Physical chemistry is kind of the physics of chemistry, like why do reactions happen and that kind of a thing. This is a very difficult subject. Both of these kind of are. In my undergrad, all the pre-med people had to take biochem, and they complained about how tough that course was. And all of us regular chemists had to take physical chemistry, and we talked about how difficult that was. Give you an idea, my first test in physical chemistry, I got a 65 and it was a B. So the professor curved the heck out of it because everybody did so poorly. It's tough material. We won't be doing any of that, so don't worry. And we're just dipping our toes into biochemistry. So we're not going to get heavy duty. Don't freak out about that. But anyway, so I had no biochemistry before a year ago. And I just found it absolutely fascinating how, I knew all this other chemistry, but seeing how it actually works inside the body is just really fascinating to me. It's like a whole new world opened up. I'd like to learn more. And, one of the things I realized, I was telling my family, is we're basically sugar factories. I mean, our bodies run off of sugar. Everything breaks down to sugar. And this is why we crave sugar and like sugar so much. And so we're all just sugar machines, pretty much. Sacks of sugar, watery sacks of sugar. So we'll be focusing on organic and biochemistry. Organic hydrocarbon is a molecule that's primarily made up of carbons and hydrogens, hence the name hydrocarbon. And it's saturated, it only has single bonds. And it will have the formula of CN, this is the most math you're going to do, CnH2n plus 2. So if this is 3, then this is going to be 3 times 2 is 6 plus 2 is 8. So it'll be C3H8 if there are no other things in there. You do have what are called hydrocarbon derivatives that have other elements in them, which we'll be talking about shortly. But a pure hydrocarbon is just carbon and hydrogen. And if it's saturated, it's only single bonds. Why is it called organic chemistry? Well, because initially they thought that all carbon compounds came from living organisms. They later found out that wasn't true. There's actually organic compounds that are not organic. I put some down here at the bottom. Carbides, like here's an iron carbide, that's an inorganic compound that has carbon in it, just Fe3C. Carbonates, like sodium carbonate, is also not a organic compound. It doesn't come from an organic living system. Cyanide is like the opposite of living, right? You know, cyanide will kill you fast. We'll talk about that more when we get into the biochemistry side. But that's just a hydrogen, a carbon, and a nitrogen, and this is very deadly. You just need a little bit and you're gone. You're a goner. So it's not really true, but the name just stuck. And so it's been called organic chemistry since the early days of the field. Not, like I said, not all carbon compounds are organic, but most are. Organic compounds have one or more atoms of carbon that are covalently linked to other atoms. We'll be talking about what this covalent means in a minute, but you guys probably had ionic and covalent bonding in your previous chemistry class. You might not remember it all, but we'll go over it again. Some common atoms that will be in hydrocarbons is hydrogen, nitrogen, oxygen, sulfur. Phosphorus is very big. Phosphorus and oxygen both are huge in the biochemistry area in our bodies. And then you've got your halogens, fluorine, chlorine, bromine, and iodine. Iodine not so much, but these can also very frequently are in organic carbons. There's more than 7 million organic compounds in the world. And carbon is called the wonder element because it bonds with so much stuff. And this is why it's very hard for us to think of like life forms on other planets being based on something other than carbon, because carbon is such the wonder element that it's just kind of hard to imagine. Some scientists have like speculated on a silicon-based life form because silicon is very close to carbon in its behavior. But carbon is just this incredible element that just, it's an extrovert. It likes everybody. And so it'll bond with everybody. So yeah, there's about 1.5 billion inorganic compounds in the world, and there's over 7 million organic compounds in the world. And here's an example of producing an organic compound from an inorganic compound. So this is ammonium cyanate, and it reacts with heat to give you urea. This is a chemical that is in urine, hence the word urine. And this is an organic chemical that's produced from an inorganic compound. So applying heat to that will form an organic molecule. So we see here a periodic table. Carbon sets right here. I think I have to click here, yeah. So this side, everything wants to get to be the same structure as this, this far column over here. So these guys tend to lose electrons to get over to here. And the other side, they tend to gain electrons to go up. So 3, lithium will lose an electron to have the same configuration as helium. Sodium will lose an electron to get the same configuration as neon over here. But fluorine is going to want to pick up an electron to become more stable like neon. And chlorine in like manner will want to get one to become like argon. So this side wants to take an electron, this side wants to give one up. Carbon's kind of in the middle, and this is why it bonds so well with everything. And the same with silicon, like I said, it's very similar in its orientation. So it bonds well with both sides. So we do have different types of chemical bonding. We're not going to go through all of them in this course. The ionic bonds is atoms donate electrons. Are we allowed to print these slides? Yes, the slides are on Blackboard. You can do with them what you will. You can draw mustaches on my face or whatever you want to do. In an ionic bond, atoms donate electrons, and then they bond together with electrostatic forces. So there's like an electrical intensity between the two of them. Covalent bonding is where atoms share electrons. There are some other types of bonding, which we're not going to get into. And the reality is all bonds are to some degree ionic and covalent. So we tend to simplify things, but the reality is never as simple as we make it, right? You know, this is true with like light, right? Light is both a wave and a particle. How the heck that is, we don't know, but anyway, it's there. All bonds to some degree are ionic or covalent, but we tend to talk about them as one or the other. And bonds form between atoms because they then are in a lower energy state and therefore are more stable. Basically, what I always say is nature is lazy. You know, water flows downhill because it's easier to flow downhill than uphill. And atoms will combine because they now have a lower energy state than they had before. So just as most people are lazy, at least I am, atoms are lazy too. So here's a little GIF that I found that shows this ionic bond. This is the formation of sodium fluoride. The sodium atom is donating an electron over to fluorine. And then now you've got a positive charge on the sodium and a negative charge on the fluorine. And they're attracted to each other because of that positive and negative charge. That's what's meant by the electrostatic attraction. So in a sodium fluoride crystal, you've actually got sodium ions and fluorine ions that are bonded together with one another. And this is also true of sodium chloride, which is common table salt. So this is a picture of sodium chloride. The sodium are these little purple balls, and the green ones are your larger chlorine. And the sodium gives up an electron, the chlorine accepts it, and then they form this lattice work like this cubic structure, because they just keep stacking on top of each other with these attractions between them. And this is why table salt is crystalline. You know, if you look at a grain of salt closely, you can see it's angular and, you know, like that. It's because it's this structure of these molecules together. I gotta figure out and keep an eye on the time too, so you guys help me too. I think we said we were going to take a break at 6:55. Is that right? So yell at me if I go over. Also, I forgot to say this. As you could probably tell by now, I'm a very informal person. Pipe up, ask questions, you know, whatever. And if you post it in chat and I'm not responding to it, yell out at me, let me know, because I probably didn't see it pop up. And we'll deal with it. So if you look at the electronegativity of atoms, you see here that covalent bonds tend to occur when the difference between two atoms is less than or greater than 2.1. So you see over here the electronegativity of carbon is 2.5 and hydrogen is 2.1. So 2.5 minus 2.1 is 0.4. That's less than 2.1. This is going to be a covalent bond. If it's greater than or equal to 2.1, it's most likely ionic. And here you see our table salt again. Sodium is 0.9. Chlorine is 3. 3 minus 0.9 is 2.1. This is an ionic bond. So this is one way of telling whether you're likely to have a covalent or an ionic bond. I guess I also didn't talk about the exams as well. The exams, you are on the honor system, that this is a closed book when you're taking it. I also ask that you don't share answers or questions with anybody. Again, let everybody have a fair shake at getting tested themselves. Anything else I need to say about that? I should probably put this in a slide. But you guys know this basic stuff, right? So, any questions here about electronegativity? Oh, this is why I thought of exams. If there's something like this that you need to solve a problem, it will be given to you in the exam. So you don't have to have cheat sheets or anything like that. Were I to ask you something like this, an exam, I don't even remember if there is one or not, but you would get this, and then it would, ask you the question, and you'd have this to reference. So that's why I started thinking about exams.
What are these units? Sorry, what were the units just on these numbers here?
Or
Or is there just
I don't
no?
remember.
Okay.
I'll have to look that up.
Okay, so it's not important then, right?
That's a really good
For us to
question.
know.
Yeah, they're electronegativity units. Yeah. Yeah, that's interesting. I'll have to look that up. Yeah, I think it's basically just a value. So yeah, it doesn't matter.
Okay, thanks.
So here's covalent bonding. This is a water molecule. So you've got a hydrogen, 2 hydrogens. This is what was on the floor in that picture. And you've got 1 oxygen. Oxygen has 1, 2, 3, 4, 5, 6 electrons in its outer shell. Oops, so it wants 2 more. So it's, instead of pulling this one away, because it doesn't have enough electronegativity to do that, instead they just share this electron, which we see over here, and it shares electron with the other hydrogen atom. And so this is your H2O, and this is a covalent bond between them. So these electrons are kind of going like this around both of these atoms, rather than it being completely pulled away like we had in the ionic bond example. And here's another example of just hydrogen does not usually exist in nature by itself, because that 2 electron outer shell is lower energy. So you almost always get hydrogen as H2. And again, they're going to each share their electron, and this is a much more stable configuration than just floating around like this. And so they're sharing these 2 electrons. Any questions there? And carbon makes 4 bonds. And the reason for this is, if you remember your electron configuration chart days in the previous class, the configuration for carbon is 1s2, 2s2, 2p2. So this outer 2 shell has 4 electrons in it, but this p shell wants to have 6. So in order to, so this, the 1s is full, 1s2 is full, 2s2 is full, but it's 2p6 to be completely full. So it wants 4 more electrons in order to fill this these p orbitals. And so in order to do that, carbon typically makes 4 different bonds in order to fill up that outer shell. And having a full shell is more stable. So S shells hold up to 2, P shells hold up to 6, D hold up to 10. So this P shell wants to get 6 total. So there's 4 opportunities to bond there. And here's some examples. So here is a carbon bonded with 4 hydrogens. This is methane. This is actually the simplest alkane. This is a saturated alkane because it's carbons and hydrogens with single bonds. So it's saturated. Here is propane, 3 carbons. This carbon here has 3 other hydrogens on it and then a carbon, so it has 4. This one here has 2 carbons and 2 hydrogens, so it's bonded to 4. And this one has a carbon, again, just like the other side here, and 3 hydrogens, so it has 4. So all 3 of these carbons have 4 bonds with something else. This is propane, another saturated alkane and hydrocarbon. It's all single bonds, and it's all carbons and hydrogens. And so this is your, if you're, I never watched it, but is it King of the Hill, propane and propane accessories? So this is your propane and propane accessories right here. We will get next week into unsaturated hydrocarbons, but here's just an example of them. This is pentene. You've got 5 carbons. That's hence the pent, like pentagon. And but here there's a double bond. So this carbon right here has 1, 2, 3, 4 bonds still. It's just that it has 2 with this carbon. This guy still has 4. It's got 1, 2, 3, 4. This carbon has 1, 2, 3, 4 as well. And this one has 1, 2, 3, 4. And this one has 1, 2, 3, 4. So it's still all 4 bonds. It just happens that these 2 carbons have a double bond with each other. And this is an alkene, which we'll talk about more next week. And then this is 2 carbons with triple bonds between them. And there's 6 carbons here. There's 1, 2, 3, 4, 5, 6. We'll get into this way of drawing chemicals in a bit here. But there's 6 carbons. These peaks are carbons. It's kind of a shorthand. But here you have a carbon that's got 3 bonds with that carbon and just 1 with this carbon, so it's still 4. And this carbon has 3 with that one, and then it's got 1 with the carbon that's right here, so that's also 4. So they're still all 4 with each carbon. It just happens that there's a triple bond there. And these are called alkynes. And so it's hex, like a hexagon, because it's 6 carbons. So just some examples. All right. Hydrocarbons can be polar and they can be non-polar. So if you have all carbons and hydrogens, it's non-polar. There's no partial positive or negative charge on any of the atoms there. So methane is an example of a non-polar compound. If there's any other atoms other than carbon or hydrogens, then it's going to be polar. This is a simplification, but for the purposes of this course, this is good enough. So you see here this oxygen this oxygen is very electronegative. It's going to pull electrons closer to itself than this carbon. You think about this as like a tug of war. You know, this oxygen over here is Arnold Schwarzenegger, and this carbon here is Dave Spader or somebody like that. And he's pulling the electrons much closer to himself. They're still sharing them. It's a covalent bond, but you're going to have this partial negative on this oxygen and a partial positive on this carbon because of that. And this causes this what's called a dipole moment. And so it's usually rendered as a Greek lowercase delta minus or plus. I don't know why I didn't put the plus in here, but I should have. But anyway, so this is a polar organic compound. This is a polar. This is ethanol. Everybody's favorite chemical. It's the active ingredient in beer, whiskey, wine, everything else like that is ethanol. So the world's favorite chemical, and it is a polar chemical. So any other atom other than carbon and hydrogen, it's going to be polar. How are we doing? And there are different ways of depicting the structures of compounds that we will use in this class. We really won't use the Lewis structure so much because it's a pain in the tuchus to draw. But you guys probably did these in your previous chemistry course, where you're actually showing all the electrons that are being shared around. This is named, I could have put that in my history moment. Who Lewis was. Ooh, I didn't think of that. There's a chemist by the name of Lewis who developed this approach of drawing structures. Ones that you're probably more familiar with are these stick structures, where you draw just a line that shows that the electrons are being shared with one another. Here's our propane again. But quite often, especially in organic chemistry, you'll just get a line diagram like this. It's also often called a skeletal formula. So this is propane as well. There's one carbon here, one carbon at the bend, and another carbon down there. So every time it changes direction, kind of, and on the ends is a carbon. So this is propane, just like this. It's just a shorter, even shorter hand. And the hydrogens are implied, right? This is telling you, you got 3 carbons and everything else is hydrogens. And then, of course, you can write just the formula of the molecule. So C3H8 is propane. You got 3 carbons and 8 hydrogens here. Or you could write it out even a little bit longer, is you've got this CH3, CH2, CH3. You can write it out this way as well. These are called condensed formulas. Any questions there at all? This all pretty much review, I would imagine, for most of you. Depends how long ago you took the class. So we are at 6:56. So what did I say? We're at chemical structures. I need to print this slide off myself so I can remember what I said the time range was. So we're gonna take a 15-minute break, go get snack, drink, go to the bathroom, whatever you want. So we will start back probably at 7:10, and I'm gonna pause the recording again if I remember how. There we go. All right. Awesome. All right. Well, I can't tell if most of you are back or not since you're all off, but we will at 7:10, so we will begin again. So any questions over what we've covered so far at all? Nothing? Okay. So here's kind of what we just talked about. Organic compounds are hydrocarbons and their derivatives. Hydrocarbons are compounds containing only carbon and hydrogen. You can have saturated hydrocarbons, which are all single bonds, like our methane friend over here. Or you can have unsaturated hydrocarbons, which have double and triple bonds, like our hexyne example here. And then you can have hydrocarbon derivatives. Ignore these chapter things. That's not our book. I must have grabbed this off the internet. But hydrocarbon derivatives are compounds that have other things other than carbon and hydrogen in them, like our example of ethanol. So this is considered a hydrocarbon derivative. Hydrocarbons can exist in chains as well as rings. So we've seen examples so far of chains. Here's our pentene with our 5 carbons with a double bond in there, all in a nice chain. But you can also have these bonds happen in rings. This is a very common organic chemical called benzene, as the formula C6H6. Notice that it's not C6H12, 13, 14, right? Because you're getting it put into a ring structure. So you're not going to have as many hydrogens on it. And the way benzene is structured, you don't have to worry about this, just to give you an example. You've got alternating double bonds in this ring of carbons, and then the remaining bonds are with hydrogens. And it is oftentimes rendered like this to indicate those alternating double bonds, and they just leave the hydrogens off because they're presumed. And sometimes it's even drawn just with a circle inside of it like that to indicate that it's a benzene ring. We're going to see lots of benzene. Benzene, by the way, is back in the day, I don't know if any of you are old enough to remember leaded gasoline. Probably not, but back in the day, they used to add lead into gasoline to make it burn cleaner and more efficiently. And but lead is very toxic to humans. And so that's why they went to unleaded gasoline. So when they first did that switch over, you could find both leaded and unleaded for a while at the gas pumps. And always had to be careful which one you were putting in your car. Benzene is an additive that they put in to take the place of lead, as well as many other compounds, but benzene's one of them. Benzene happens to be a carcinogen. It causes cancer, but it completely burns up in your engine, so you don't have to worry about that. But I wouldn't go around drinking unleaded gasoline for a number of reasons, one of which is it can cause cancer. But benzene is also used in the distillation of, no, I would take that back. Is it benzene or carbon tetrachloride? I think it's carbon tetrachloride. Carbon tetrachloride is a carbon with 4 chlorines on it. And that was used in the dry cleaning process back in the day. But it's also a carcinogen. It's also used to distill alcohol, ethanol, to get it pure and pure. And so you get higher alcohol content. And there were a lot of organic chemists back in the day who came down with cancer because they were drinking lab ethanol, and they were getting traces of this carcinogens in their ethanol and giving themselves cancer. This is back before they realized these things were cancer causing. But anyway, they can form rings. Here's an example of a benzene ring. It's got a couple chlorines out here. There's a little chain in here as well with 1 carbon in the middle here that's connecting these 2 different rings. and they can get much more complicated than this, but this is just an example. So you can have hydrocarbons in both chain format and ring format. And the reason, again, for forming rings is it's a more stable configuration depending on how big this chain is and how many substituents other than hydrogen you have involved and all that, but they quite often are in a more stable environment if they're in a ring, and they'll tend to form a ring structure because of that. Lower energy. Isomers are compounds that have the same molecular formula but a different structure. And so here we have an example of a butene, and this has 4 carbons, 1, 2, 3, 4. This has the prefix but. We'll get into this in a minute because it has 4 different carbons. And it has the formula C4H8, but so does this. This is called cis-2-butene, and it's cis means it's on the same side. So these methyl groups are on the same side of this double bond, and so this has a different structure than one that's in a trans formulation. So trans is where your functional groups are on opposite sides of the double bond. So if you drew a line down through the middle here, you've got these on opposite sides. So this is trans. This still has the formula. Excuse me. I got something caught in my throat. This still has the molecular formula C4H8. Oh boy. But it is a different configuration. See the difference there? So these are isomers of one another because of that. Another example is butane and isobutane. Both have the formula C4H10. Here you just got 4 carbons all in a nice row. Here you have 3 carbons with 1 methyl group hanging off the end. So isobutane has the same formula as just regular butane, but they can have very different chemical and physical properties from one another, even though they have the same molecular formula. We're going to talk more about this stuff, but any questions there? And here's an example that's more in the biochemistry realm of things. So you guys have probably heard about trans fatty acids and how bad they are. If you look at a lot of labels on food, it'll say no trans fats and things like that. The reason for this is that cis fatty acids, so here you have a fatty acid that's got a double bond here, and the hydrogens are on the same side. So it's in a cis configuration. Cis fatty acids tend to be oils, but trans fatty acids, here we've got the double bond, but now the hydrogens are on opposite sides. So this is in a trans configuration. These tend to be solids, and trans fatty acids is the bad one that contributes to heart disease. And when we get to the biochem stuff, we'll actually see why this is. But this is why trans fats are bad, is because they cause heart disease. And most fatty acids occur in nature naturally in the cis formation. But when they go through a lot of industrial processing, so processed foods, they tend to end up converting them into trans. This is why a lot of processed foods are kind of bad for you, is you get a lot of trans fats in them. And this contributes to heart disease. But anyway, these two, again, are isomers of one another. They're just big chains of carbon with some oxygens on the end here. And they are isomers of one another. One is cis, one is trans, but they have the same molecular formula. But yet here you can see there's even a difference in the health effects of these two different things based on this configuration. Okay, how do you name alkanes? We're supposed to go to 740. Okay, so I gotta try to get through all of this. So alkane names, these are the prefixes that have been defined. IUPAC is the International Union of Professional something chemists. I forget what the A's, Professional Association of Chemists, maybe. But this is an agreed upon naming convention for these things. So 1 carbon is a meth, 2 carbons is an eth, 3 is prop, 4 is but, 5 is pent, like pentagon, 6 is hex, like a hexagon, hept, oct, like octagon, known, and dec. That's as big as we'll get in this course. So methane, we already saw, is just 1 carbon and 4 hydrogens. So that's where the meth comes from. And then the ane ending means that it's an alkane that's all single bonds. Ethane is 2 carbons with the rest being hydrogens. And that's got the eth. Our propane and propane accessories has got 3 carbons together along with the associated hydrogens. So these you're going to have to become familiar with. You're going to need to know these in order to name chemicals. If it's a group, if we go back to our example here, this isobutane, it had this carbon with 3 hydrogens hanging off of this main chain. So this gets treated as a functional group. And because it's just 1 carbon, this is called a methyl group. And if there was 2 carbons, it'd be an ethyl group. So we go back here, you see 1 CH3 is methyl, ethyl, propyl, butyl, pentyl, hexyl, so forth and so on. Okay, so the first rule when naming an alkane is you find the longest chain that you can make of carbons. So in this example here, I got 1, 2, 3, 4, 5. I could go 1, 2, 3, 4, 5 as well. I could go 3. Obviously, that's too short, so we're not going to use that one. Go with this one because it's the straightest chain. So we'll go with these as our 5. So this is going to be your main chain, and this is going to be your functional group that's hanging off of that. In this case, the longest you can get, you can't just go straight because that gives you 1, 2, 3, 4. But if I go this way, I got 1, 2, 3, 4, 5, 6. So this is going to be a hex with this guy being a functional group. So you're looking for your longest chain that you can form. The second rule is you number your carbons and you start numbering closest to the functional group if there is one. So here we've got this functional group hanging off here. We want that to be the second carbon, so we start numbering from this side, because if we start over here, this would be the 5th carbon, or the 4th one, 1, 2, 3, 4. This would be the 4th carbon. We want the lowest number, so we'll start on this side and number this way. Everybody see that? And then in this example, again, we want this number here to be the lowest that has the functional group on it. So we're going to go with 1, 2, 3 rather than 1, 2, 3, 4, because then this will be a larger number there. So you want to go with the smaller number that you can get. In this example, we have 2-methylpentane. This is correct because you've got the smallest number. Instead of numbering it backwards, which would make it 4-methylpentane, you want to go with the lower number. So we go with this numbering instead of this way. Does that make sense? Any questions there?
Wait, why wouldn't you do 1 if you want to do the lowest number? Like, why would you do 2?
Well, it's on the second carbon, right? It's not on the first carbon. So you want this to be on the lowest number that you can get. It's just a naming convention, really, nothing else. So because this is, if you start here, this is going to be 2. But if you start over here, this is going to be 4. So you want to go with the 2. Does that make sense? You just want to have the lowest number that you can have. Or did I lose you?
So the bottom one would be 3-methylpentate then, or methylpentane?
This one here?
Yeah,
Well, it's 1, 2, 3, 4, 5, 6, right? So this is going to be 3-methylhexane.
oh, right, okay,
We'll get into that in a minute.
I gotcha.
But yeah, so you're going with you're numbering from this side, so you get this number to be the lowest. You guys will see this. We'll keep going. All right, if there's only one functional group, like in our example so far, then you name and you number that functional group, and then you prefix it to the parent chain. So here we have 5 carbons, so that's going to be pentane, and then now it's 2-methyl, because it's on the second carbon, so this is 2-methylpentane. So this tells you exactly how to draw this. If I were to give you this on a test, you ought to be able to draw this out and know how it looks based on that name. So that's really why it's just a naming convention so that people can communicate with one another, basically. And then here, like we just said, this is 3-methylhexane because this methyl group is on the third carbon in the chain. And so this gets named 3-methylhexane. If there's 2 of the same group, then you combine them and you use your typical mono, di, tri, tetra, penta, hexa, so forth and so on, like you're familiar with in other circumstances. So in this example, we have 5 carbons here. So this is a pentane. But now I've got a methyl group on the second carbon, and I have a methyl group on the 4th carbon. So this becomes 2,4 dash dimethylpentane. So the di telling you that there's 2 of these, and of course the 2 numbers tell you there's 2 of them as well. But again, you want to number this main chain such that both of these can be the lowest numbers you can get. Sometimes it doesn't matter. Like in this case, you'd go 1, 2, 3, 4. It's still 2,4 dimethyl. So in this case, it doesn't matter which way you number them. But
So is the dimethyl like just the compound of what it is, and then the pentane is because there's 5?
Well, I wouldn't say it quite that way. This whole thing is the compound. What this is telling you is you have a pentane chain, 5, with 2 methyl groups hanging off. So that's where the dimethyl is coming from. It's telling you.
That makes sense.
Right? That makes sense. Here, they're both on the same carbon. So again, you still have 5 carbons in the main chain. So that's a pentane. And then it becomes 3,3-dimethylpentane. So that tells you that they're both on that same carbon. That makes sense? And the
Yeah,
di,
thank
of
you.
course, is indicating that there's 2 of them. If you have 2 different kinds of groups or more, they get numbered separately and you order them alphabetically. So here we still have our pentane chain, 5 carbons. We've got a methyl group on 2, and we've got an ethyl group on 3. So but now you organize them alphabetically. So this is 3-ethyl, 2-methylpentane. So you put the E before the M. And with our example of 2 groups here, so in this one we have 8 carbons, so that makes it an octane. But I have 2 propyl groups here, one on the 4th carbon, one on the 5th one. Propyl because there's 3 carbons in this chain. So this is going to be 4,5 dipropyl because there's 2 of them. And then here we have an ethyl group, and it's on the 3rd carbon. So this is going to be 3 ethyl, 4,5 dipropyl octane. And again, because the E in ethyl comes before the D in dipropyl, then it comes first. I probably should have made this like a.
Doesn't D come before E in the alphabet?
Pardon me?
Doesn't D come before E in the alphabet?
Oh yeah, you're right. Yeah, I'm sorry. The di does not.
The die doesn't count. Like
Isn't
you're
counted. It's the propyl part.
okay.
Sorry, I
Um,
said that
I
wrong.
have a quick question, sorry. I think I missed something. So how are you figuring out whether it's like the methyl or the ethyl or the dipropyl? Like how do you know that this, like on the bottom strand, the blue one that's on 3, how do you know that's ethyl?
So the first thing you're doing is you're finding your longest chain, right? So I can make 8 by going all the way across here. If I went this way, I got 1, 2, 3, 4, 5, 6, 7. So
Okay.
if you made this your main chain, that's smaller than 8, right?
Mm-hmm.
So, and then here you've got 1, 2, 3, 4, 5, 6, 7, 8. So you could do it this way. That's possible. But usually people just do the straight chain if you have an option there. And so you pick your longest chain first, and then everything else that becomes functional groups.
Okay.
So this is octane because there's 8. So octane tells you this whole string right there. And then you look at what's hanging off of those functional groups. I'm sorry, what's hanging off of that main chain. Does that make sense?
Yeah, so because there's 2 hanging off of the 3, it'd be ethyl.
Mm-hmm.
And then, okay, that makes sense.
3, there's propyl.
And they don't necessarily have to be the same, as long, it just matters how many there are.
Yeah, I think that's where I was getting confused, as I was saying like there's CH2 and then CH3, and I thought that you were naming them by that instead of the amount. So
Oh, I see. You were thinking this was ethyl?
yeah.
Yeah. No, methyl is, we go back here. I know you haven't had much time to digest this, but that's okay. A CH3 is a methyl group. A CH2, CH3 is an ethyl group. And the reason why there's 2 here is because this is going to bond with something else, right? It's going to connect into the chain. So that's why there's only 2 hydrogens here. And that's why you don't have your 4th one is where this carbon is connecting into your chain. So it's
And
the
will there
number of
ever-
carbons that you have.
Okay. Is there ever gonna be a chance that, so for like the second one, ethyl, is there ever gonna be a chance that the CH3 is gonna be before the CH2, and is that gonna change it? Or does it not matter the order?
But you can't do that because then you'll have 5 bonds on that carbon,
Okay,
right?
thank you.
Yeah, so that's why you'll never have that. No, these are great questions. Please ask questions.
Going back to the 3 ethyl 4,5 dipropyl octane, when you're looking at that, are you numbering based on alphabetical, or are you numbering based, so because it looks like obviously you started numbering from right to left, so you numbered to include the ethyl first?
So the rule is you want your first functional group to have the lowest number.
Okay, so it's just first functional group in general. Okay.
Right. So that's what you go with. And then here is just about punctuation. You're going to separate numbers with commas if you have two together like this. And you separate numbers and letters with hyphens. And then you do not add anything between the last named group and the chain name. So here we have 4-ethyl. So this is telling you that I've got an ethyl group, 2 carbons at the 4th position. 2,3-dimethyl, so I've got 2 methyl groups, 2 singular carbons on the 2nd and the 3rd carbon in the main chain. And then I've got a propyl group at the 5th one. And then nonane tells you there's 9 carbons in that main chain. Do I draw this out or no? You guys want to see me draw this out? No? Or you got it? I don't want to beat a dead horse, but I can draw it if you want me to.
Yes, please.
Okay.
Yes,
So,
please.
annotate. So yeah, so what this is going to be, got to get used to my pen. So we're going to have 1, let's draw it upside down. All right, 1, 2, there's 9, right? Nonane is 9. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9. So the nonane tells me my main chain has 9 carbons and hydrogens in it. Then I've got this 4-ethyl. So let's see here. So if I start on this end, you just got 1, 2, 3, 4. So here, that's a straight line. You're going to have an ethyl group like this. And then on the 2nd carbon is a methyl group. So you're just going to have a CH3 hanging off here. And then the 3rd carbon is also a methyl group. So we're going to have a CH3 here. Or we can just draw a C. The hydrogens are implied, right? So this is 2 carbons here. Sorry, this isn't the best drawing. On the 2nd and 3rd one. And then on the 5th one, so we've got 1, 2, 3, 4. I've got a propyl group, so that's going to be 3. 1, 2, 3. And there is your 4-ethyl, 2,3-dimethyl, 5-propyl nonane. Are you able to follow that? Ignore my backwards C over here. No. Any questions there? I'm going to give you one to try here in a second, so we'll be good. All right, let me turn the annotate off. Oh, I lost my, are you seeing my cursor? Oh, I got to clear off the, oh, there we go. Got it back. All right, I need to clear off my annotation. Clear all drawings. There we go. And stop. Okay. All right, so that's just the punctuation of this. So if you got a comma between if you've got 2 or more in here, then you're gonna have commas, hyphens everywhere else, except at the very end, there's no dash. I don't think that I make you guys, I know some instructors are like really picky about this. I'm not super picky. So, and I might not even done it right in the test. Hopefully I did. Most people have complained I fixed it, but You know, like if you let's say you were writing this out by hand and you happen to capitalize this in and no name, I wouldn't mark you down for that. Some professors would. I wouldn't bother. But anyway, this is just the punctuation we use. Here's my history highlight, my first one. Woo-hoo. So I mentioned IUPAC. Oh, I was totally wrong. It's International Union of Pure and Applied Chemistry. So this is the modern day organization that,
I'm reminding you,
among other
take calcium.
things, defines nomenclature for chemical compounds. Its predecessor was a Geneva Convention, not the
I'm reminding you,
Convention on War,
take
but the
calcium.
Geneva Convention on chemistry. In 1892, there was an International Congress of Chemists that met in Geneva, Switzerland, and they developed what was called the Geneva nomenclature. And this became the core of what is used today. It's changed over the last century and a half, but it was the core, predecessor to that. And by the way, when I did chemistry, if you're majoring in chemistry, you used to have to take German. And I did 2 years of German in undergrad because Germany was like a leading country in chemistry back in the 1800s. And nowadays it's become, there's, a broader spectrum of that. Russia's really big in chemistry, so is Japan. But that's why we had to take German, because a lot of the important literature was never translated into English. So I actually had a course in grad school where I was reading a German, resource manual in German. You need to be able to do it for that reason. So Germany was really big into chemistry back in the day. And so this is where we get the suffixes come from Greek. This was proposed by a chemist by the name of August Wilhelm Hofmann. Nice German name. He lived from 1818 to 1892. So he died the year this convention met. He was also a linguist, like me. He loved languages. I do too. And so he took the vowels A, E, I, O, and U, and he proposed ein, een, ein, on, and un as endings. So alkane is what we're talking about tonight. And the I-N-E, een, was later changed to ein, like the hexine I showed you earlier, the triple bond. Un never really caught on. That never really got used, but he proposed doing that. And these suffixes actually mean in Greek daughter of. So een, this is really in Greek ene and ode, all are suffixes that mean daughter of. So it's like they derived these compounds from other compounds. So they were thinking of them as daughters of the parent compound, if that makes sense. So again, you're not getting tested on this, but a little bit of history there for you. Somebody had their hand raised.
You just answered my question.
I did?
Yeah, I was wondering if this is going to be on the tests or not.
No, I won't test you on this. I don't know. Oh, by the way, I do get asked every semester about extra credit. The chemistry department does not do extra credit. I'm not allowed to give you extra credit. So sorry about that. I should put that in my slide as well. Okay, there are common names back before they got this nomenclature established. There were people that established kind of common names for alkanes, and they are still sometimes used to this day. I noticed in a lot of in the food industry in particular. So iso is one of these. I showed you the example of isobutane. And iso is used when you have a methyl group attached to the second carbon in a chain. So you've got this chain here like this, and then you've got this benzene ring hanging off of this. Because you have this on the second carbon, this is often called isopropylbenzene. This is not the IUPAC nomenclature, but a lot of times you will see this. So you guys have heard of isopropyl alcohol. You probably got that in your cabinet for cups and stuff, right? And this is isopropyl alcohol. So the alcohol group is on that second carbon in the chain. And so it gets called isopropyl. If this alcohol, this OH here, was up here, it would not be called iso. It would just be propyl alcohol. So this is what you're actually using when you use that out of your cabinet for cups. The isobutane, again, is you've got 4 carbons here, but this is really propane by the IUPAC naming convention, and it's on the second carbon. So the formal name is 2-methylpropane. You've got this this methyl group on a propane chain on the second carbon, but a common name for this is isobutane. So you will encounter this sometimes. Like I said, it seems like it gets used a lot in the food industry, I've noticed. You know, I look at packages, sometimes I get curious and look at the chemical contents, and but you see a lot of times that they'll do it with food. I guess medicine as well. You'll see a lot of it, like isopropyl alcohol. You'll see that in the medical field as well. Since a lot of you guys are going into medical or dental type fields, that's why I want to point this out. So if you see these things, you have an idea of what they are. Neo is another one that gets used. Neo means new. And this is where you've got 2 methyl groups are attached to the last carbon of the chain. So here you have a carbon, and you've got a methyl group here and a methyl group here, or second to last carbon of the chain, I'm sorry. So this is called neo. So this is often called neopentylbenzene. So you got a benzene ring here. Don't worry about this too much, but you got a benzene ring over here, and then you've got this carbon chain coming off of here. 1, 2, 3 carbons with these 2 carbons hanging off the sides. Because it's on that second to last carbon, the common name was neopentylbenzene. We would call this 2,2-dimethyl-1-propylbenzene, but this is a common name for it. And neopentane is another example. We would call this 2,2-dimethylpropane, because you've got this 3 carbon chain with 2 methyl groups off the side. But sometimes you'll see neo. Not a whole lot. Neo is less common. Iso is very common with that. And speaking of carbons, we have different types of carbons. There are primary carbons, which is a carbon that's attached to only one other carbon. So that would be a carbon on the end here. This is a primary carbon. A secondary carbon is attached to 2 other carbons, and this sometimes gets the prefix sec for that reason. So like this guy here, that's a primary. That's 4 right here. This guy here is attached to 1 carbon in this chain, this ring, and it's also attached to 1 carbon over here. So this would be considered a secondary carbon. Tertiary is to 3 others, and quaternary is you've got a carbon attached to 4 carbons. And so here we have an example. So this is a primary carbon because it's only attached to 1 other carbon. This one here, though, is secondary because it's got 2 carbons attached to it. This one is also a primary because it's only got 1 carbon attached to it. But here you have, this one is a tertiary because it's got 1, 2, 3 carbons attached to it. Everybody following this? And then if you have something like this, you've got 4 carbons attaches one carbon. So notice this carbon has no hydrogens on it at all because all four of its bonds are with other carbons. And then these methyl groups out on the side. This is called a quaternary carbon. These names get used, again, as kind of more common names. So like here, this is called tert-butyl alcohol because this alcohol is on a tertiary carbon. And this is called sec-butyl benzene because this benzene ring is on the second carbon, the secondary carbon in this chain. Okay, so here's a naming practice one. I'll give you guys a few minutes to try to name this compound. When you're done, you can just type the name in the chat if you want. We'll see how everybody does with it. So give you a few minutes to look at it. All right, you are rolling in. Somebody named it 2 comma oops. I'm just joking. Okay, looks like the consensus here. Yes, this is 2,3-dimethylhexane. So your biggest chain is these 6 carbons. So this is your hexane. And then on the second carbon and the third carbon are your methyl groups. So it's 2,3-dimethylhexane. And you don't number from this side because this would become 1, 2, 3, this would become 4, 5 dimethylhexane. That's larger than 2, 3. So you go on this end and go back this way. Any questions there? Here's another one for you. Go
I
ahead.
was going to ask if that D in the dimethylhexane needs to be capitalized.
Yeah, that's what I was saying. I wouldn't mark you guys down if you did that because I did it. Look at that.
Okay.
Shame on me.
Thanks.
Looks like we're building a consensus again. So yes, we have 3-ethyl-5-methyl octane. So you've got your 8 carbons along here. And you've got this ethyl group, then we start numbering from this end is on the 3rd carbon. And then this carbon is on this methyl group here is on the 5th carbon. So you get your 3-ethyl, 5-methyl octane. Good. You guys are getting it. All right, naming rings. So very similar, but a little different. So you're going to have the prefix cyclo. That tells you you're in a ring. So this is cyclopropane. It forms a triangle. You've got a carbon at each point. So there's 3 carbons. This is cyclopropane. Here is cyclobutane. You've got 4 carbons all connected together. Here is cyclohexane. You've got 6 carbons all connected together. And here's cyclopentane. You've got 5, so forth and so on. So here's your the pentagon is shaped like this. It's called that for that reason. And so you've got cyclopentane. So the naming rules are, if you just have one functional group hanging off of a ring, then there's no need to number it because it's always going to be just one. Says, I just realized that the problems are in the slides and the answers are on there. Yeah, you can cheat and look at your answer if you want that way. By the way, the problems that I put from the book, I picked problems that they're all odd numbered problems because the answers are in the back of the book. So you can check your answers that way. So anyway, if you just have one functional group hanging off of a ring, then there's no need to number it because it's just assumed to be one. If you have 2 groups on a ring, then you start numbering the carbons on the ring at the higher alphabetical group. And if you have, I probably maybe should have said lower. What I meant was higher up in the alphabet. And if you have more than 2, then you number, that'll give you the lowest numbers. So here, this is methyl cyclobutane. So you've got 4 carbons in this ring. Oops. So that's cyclobutane. And then here you have a methyl group hanging off. Remember, this is implied that you have a CH3 out here. And so you don't have to put a number here because it doesn't really matter where you stick it. It's always going to be methyl cyclobutane. And it'll always be number 1 because there's only 1 there. Does that make sense? But in this case, we have a 5-membered ring. So that's cyclopentane. We now have a methyl group hanging off of this one. But we have an ethyl group hanging off here. There's 1 carbon there, 1 carbon there. So this is an ethyl group. So now you're going to start with the first carbon being on the lower alphabetically named thing. So this becomes 1 ethyl, 2 methyl cyclopentane. That makes sense? Everybody follow that? And then here we've got 3 different groups. We've got a methyl group, and here's a propyl group. So you've got 1, 2, 3 carbons. So this is a propyl group. And then you've got a 6-membered ring. So this is cyclohexane. And then now you want your dimethyl to be, you want the methyl is lower alphabetically than the propyl. So you want those to have the lowest numbers. So we can start here and go 1 methyl, 2 methyl, 3 propyl cyclohexane. That makes sense? Cool. Any questions there?
That makes sense.
All right, try to name this sucker. Oh, and Julia, yeah, I have problems at the end of the chapter for you. You guys will see that as the last slide tonight.
Quick question.
Uh,
So when we choose which one we start at, does it matter which way we count from there or
you
no?
gotta get lowest numbers. So if it's a lower number to go right to left, then you go that way, or I guess clockwise, then you go that way. But if it give you lower numbers that go counterclockwise, then you go that way.
Okay, thank you.
And again, it looks like we're building a consensus here. And you guys are right. We have 1-ethyl-4-methyl, so we can start numbering anywhere. So we're going to go with the lower alphabetical. So this is, or I'm sorry, the lower alphabetical. So this is 1-ethyl because you got the 2 here. And then now you got 2, 3, 4, 4-methyl cyclohexane. Good job. Good job. Okay, cycloalkanes also have isomers, but there's 2 different kinds now. You have constitutional isomers, where they have the same molecular formula, but a different structure. We talked about those earlier with chains. But now you can have what are called stereoisomers. And these have the same molecular formula and structure both, but they have different orientations of the atoms in space. Remember, atoms are 3-dimensional, not just flat like we've been drawing them. And so there is a spatial element here. So constitutional isomers, all
Wait,
of
can you go back one slide?
sure. Do you have a question there, or you just want to jot it down? I'm going to show you some
I
examples.
just had to jot it down, sorry.
Okay, that's fine. Okay, so constitutional isomers, here's an example. All of these compounds have the same molecular formula, C5H10, but they all, look how different they look. You've got cyclopentane, methyl cyclobutane, so you pulled one of the carbons out of the ring and stuck it off here. That's still C5H10, so these guys are isomers of one another. Then you can have 1,1-dimethyl cyclopropane, so pull another carbon out. Now you've got a 3-membered ring with 2 methyl groups off. Kind of looks like a TP. And but this still is C5H10, so it's an isomer with this guy, and it's an isomer with that guy. You can also have 1,2-dimethyl cyclopropane, so now it's over here, but this still has the same molecular formula. And then here, this kind of looks like a base with a straw coming out of it or something, huh? Or maybe it's a candy, what do they call those, kisses, with a really long tag sticking out of the top. But anyway, this is ethyl cyclopropane. So it's still 2 carbons, it's just now in an ethyl configuration. And that is also isomers with all of these. So these are all constitutional isomers of one another. They have the same exact molecular formula, just different structures. But again, that structure is going to affect its chemistry.
So I know this is probably a dumb question, but I'm just doing it for clarification.
Never a dumb question.
Everywhere where there's like a point in a way is a carbon, right? So like on the cyclopentane, like each point is a carbon, right?
Right.
Okay.
Yeah, I thought I had an example. Did I give you guys an example of that?
You probably did. I just,
Maybe I didn't.
I don't think there was. I was going to ask if you had any examples of the drawings, just of the general structure.
but yeah, this is equivalent, you know, if we drew this out completely, you'd have a CH2, 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 right, all the way around. And here you'd have a CH2, CH2, a CH on this corner because it's got a carbon now coming off of that. And then another CH2. You guys see that? Or do you want me to draw it?
So on that methos, the one that you're on, so would the carbon be on like in the square or would it be on the other end?
Both.
So they're both carbons.
Yeah, let me draw this for you.
Okay, thank you.
So this guy right here is going to be, you can see you've got C, 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 like this, right? So you can only have 4 bonds. So this has already got 2. So this has got to have a hydrogen, hydrogen, right? This could only have 2. So you got a hydrogen, hydrogen here. It's kind of hard to draw, but I'll do it for you. Like this, right? This one as well. If I hold the pen different, it might be easier. So you get a hydrogen and a hydrogen here. But now this guy has got a methyl group. So this is coming off of here in a CH3, right? Because this carbon's got to have 4. So it's got 1 and then 3 hydrogens. That gives him 4. But now this guy's got 1, 2, 3. So he can only have 1 hydrogen here to make 4. So that's why it's CH2, CH2, CH2. But then this one is CH because you got this CH3 hanging off of there. So each one of these is a carbon right here, like this. And then up here as well. And like manner here. I really thought maybe it's coming up, but I really thought I had one like that. And the same here. This is a carbon here, carbon there. Oh, horrible. Carbon there, carbon there, carbon there.
That makes sense. Thank you.
I was just going to say something about this. What was it? Oh, yeah. So like here, just in case I don't have it on another slide. So this is also C5H10. This is also an isomer of all of these. Because you've got 1, 2, 3, 4, 5. Just it's not a ring, but it's still C5H10, right? If you drew it in this kind of a line structure to denote the different carbons, then you have to put a bend in it, and that's why you get it'll look like this. 1, 2, 3. Let's see, 1, 2, 3, 4, 5. Right? So this is the same as this. You've got carbon here, carbon here, carbon here, carbon here, and a carbon on this end. So this is the line shorthand for this compound there. Does that make sense? Or did I lose y'all?
Yes, thank you.
Okay. Cool. All right. Clear all drawings. So we can move on. I'll turn off annotations. All right. Okay, stereoisomers, like I said, these have the same molecular formula and the same structure, but they have different orientations in space. So what do I mean by that? Well, again, like I said, atom or molecules are 3-dimensional. So here I've got 1,2-dimethyl cyclopentane. So I've got this cyclopentane ring and 2 methyl groups hanging off, and I've got this carbon here and this carbon here is going to have a hydrogen as well. And this is called cis because these 2 methyl groups are on the underside of, they're on the same plane of this, on the, how do I say this? They're on the underside of that ring, right? Whereas in the case here, you've got one above the plane of the ring and one below it. And so this is going to be a trans configuration. So this is trans 1,2-dimethylcyclopentane, and this is cis 1,2-dimethylcyclopentane. And you can kind of see it if you draw it kind of on end, right? These are stereoisomers of one another, and they will have different chemical properties. Matter of fact, they make a big difference, especially in reactions in the body. We'll see this later. Sometimes these get drawn in a top-down view, and what they try to do is show, by drawing like a wedge here, they're indicating that both of these methyl groups are coming out of the plane, if you will. And then here is one coming out and one going back into the plane of the page. But these are the same as this one, it's just rendered differently. So sometimes you'll see them drawn this way as well. Does that make sense? So a wedge is kind of coming out towards you, and a dotted line is going back away from you. Any questions there? Okay. You can halogenate hydrocarbons. If you add a halogen, in this case chlorine, sorry, this is a little blurry. You add chlorine, and you either use ultraviolet light or heat. You will replace one of the hydrogens with a chlorine atom. And so you will now get chlorine on this compound, and you'll get hydrogen chloride acid as one of your products as well. So this splits apart. You've got two chlorines here. One goes onto the chain, and the other chlorine reacts with this hydrogen that pops off, and it forms hydrogen chloride. Does that make sense? What are these things called? Do you guys remember from your last chemistry class?
Catalysts.
Yeah, who said that?
Anna?
Put a gold star on your little screen there. Yep, these are catalysts. So catalysts are things that don't participate in the reaction, but they assist the reaction in happening. And so in this case, halogenation, it can be either, the catalyst can either be ultraviolet light or it could be heat. In this case, about 400 Celsius. This could be chlorine, this could be fluorine, this could be bromine, any halogen will do this reaction. So why am I saying that? Because this is how you name halogenated alkanes. And so if it's a fluorine, it becomes fluoro. If it's a chlorine, it becomes chloro. Bromine is bromo, and iodine is iodo. And these are the prefixes that you use. Like I was saying, some professors would mark you down if you wrote this. A lot of people spell this flowero because your brain just kind of goes there, right? I've done it myself, actually. So some professors will actually mark you down for that. I probably wouldn't if you were writing it out on a test. But since everything is multiple choice and all that, it's not going to matter. But anyway, it's FLUORO. So here we have 2-chloryl-3-methyl-butane. So butane, because I got 1, 2, 3, 4 is my longest chain that I can make. And now I'm going to go with numbering to my first functional group lowest alphabetically. So this is the second carbon. So this is 2-chloral. And then this is going to be 3-methyl on this 4-carbon chain. Does that make sense? And here I drew it all out with all the hydrogens and everything in there. Here's your chlorine stuck in there. Any questions there? So it just gets named like anything else. It's just a functional group that gets added in there. With a ring, you've got a 6-membered ring. So this is cyclohexane. And so now though, I've got this fluorine on here and I've got an ethyl group. So I'm going to start with the E. So this is 1 ethyl, 2 fluoral. Why wouldn't I count around this way? Because it would make this number even bigger and you don't need that, right? If I went this way, it'd be 1, 2, 3, 4, 5, 6. It'd be 1 ethyl, 6 fluoral. And that you can get lower numbers going the other way. So you go around this way. So that's, somebody was asking that a moment ago. We're going to go counterclockwise because it gives us lower numbers.
Wait, in the first one, why is it 2 chloral if there's 1 chlorine?
Because it's on the second carbon. Remember, this number here is the placement. in the
Oh,
chain,
okay.
Right. There's only 1 methyl group too, but it's on the 3rd carbon.
If something was halogenated more than that, would you do like the same Greek prefixes like dichloro and
Yep,
dichlorate?
You got it. Absolutely. Yeah. Let's try to think of an example off the top of my head. So here's one. I've got 2 halogens in there. So try to name that. And then we'll take a short break. Otherwise, I'm going to run out of time tonight. This is good. I've run out of time. I was worried I wouldn't have enough. The last 2 semesters, we only had to meet half of the 3 hours. But now they changed that. They said, no, you got to meet the full 3 hours. And I'm like, well, I covered the same material. And now I got double the time. I was a little nervous about that. And here you're seeing the little angle thing. So there's a carbon at each point here. 1, there, and there. Right. So again, looks like we're building a consensus. Yes, so you're going to go with the B over the C. So this is on the 1st carbon, and this is a hexane. There's 6 carbons in that chain. So 1 bromo, 4 chloral hexane. And see, by reading that, you know exactly how to draw this out. With common names, you don't always, you'd have to memorize all kinds of common names to even know how it's structured. So this is what's nice about the IUPAC naming convention. All right, let's take a 10-minute break. Let's be back here at 8:30, and then we'll take ourselves home from there. So 10-minute break. 8:30, we'll start back up again. I'm gonna pause recording, resume. There we go. All right, physical properties of alkanes and cycloalkanes. So solubility, they are going to be insoluble in water, but they will be soluble in nonpolar solvents. This is because they tend to be nonpolar themselves, and water is polar. So they will dissolve in nonpolar solvents. Density-wise, alkanes are less dense than water, so they'll float on top of water. Boiling point, the larger the chains, it increases the boiling point, and the greater of branching decreases the boiling point. The reason for this is is the larger the chains are, the more they're gonna like be attracted to another chain. So they'll pack kind of together and be more stable and therefore less likely to break apart as you're heating them up. But when you have more branching, they can't stack flat together anymore because there's branching going on, and so they're not as closely packed together, and they'll break apart more easily. And so as you apply heat, they'll have a lower boiling point. That makes sense? Chemical properties. Alkanes are combustible. They are flammable. The products that they produce, as with any combustion, is carbon dioxide and water. And they can also be halogenated. So as we already saw, halogens will replace hydrogens with heat and or light as catalyst. Oh, we're at the very end. I thought I had a few more slides on that. So these are the practice problems that I have picked out. This matches the material that we covered tonight. So if there's stuff in the chapter that I'm not talking about, there's no problems in there for you based on those. And like I said, these are all odd numbered so that you can check your answers in the back. And with that, we'll just kind of do, we'll get done a little early tonight, actually. If that's okay with you guys. If you want to stay and work on these problems, I'm happy to stay here for you. Or if not, you can skedaddle. Before we go, any other questions or anything from anybody?
Yeah, I just have, how do you know when you're like doing the naming thing, how do you know to look at the alkyne or to look at like the other chart?
I'm sorry, the alkyne.
Like okay, like the two charts that you gave us with like the structural formulas and their names and stuff.
Which chart are you talking about?
Like for the naming thing, it was like naming alkene chains. How do you pronounce it?
I think it's slide 30 and 31 you're talking about.
I need to put my slide numbers on here because I don't know.
Yeah, I don't know the slide numbers.
Here?
Yeah, that and then that
one?
chart. Yeah, how do you know
Yeah.
which one to like look at?
Yeah, so this is naming the main chain. So this is giving you the methane, ethane, propane. These are the functional groups that are hanging off of your main chain. So this is a methyl group, an ethyl group, a propyl group. Does that make sense?
Yes. Okay, that I didn't understand, but now I do. Thank you.
I'm glad you asked.
About the practice problems.
Pardon me?
The practice problems,
Uh-huh.
are they from the 7th edition that the course suggested, or?
Well, actually, the course says 4th edition. But
Yeah.
I think they're the same in the 7th edition, if I remember correctly. I looked at them. So I think they're the same.
Yeah, I guess I meant that WCC suggested, not the course.
Yeah, when you go on the website to like order your books, it suggests the 7th edition,
Yeah.
Really?
the 4th.
Mhm.
Yeah, because I accidentally also got the 7th edition.
Yeah, that's why I asked if the problems line up. I'm
Huh.
sure I read it anyway, and it was a lot of the same stuff. So.
Yeah, the reason, well, there could be a few little differences. So I'm teaching underneath a PhD. I have a PhD in chemistry, and she wants the 4th edition. And I asked her about it, and she was like, well, that's because they did make some changes, and I don't like them. So she's like, I always use the 4th. But
Okay.
maybe the college just went with the latest editions, probably what they did.
Probably.
But I think I compared them last time and they were the same. I hope so. If you see them not matching up or you're not getting the right answer, let me know. And we have to figure that one out. I have a PDF version of it, but I can't give it to you because of copyright.
Right.
But if you find it on the internet, I should be recording this. That's between you and whomever else, not me. But I think if I remember right, I compared them and they were okay, but I'm not 100% sure.
Okay, because I don't know if WCC has the 4th edition, but I did find it on other websites. It would just take a while to ship.
Yeah, do I still have? I'm trying to remember what version I have. I did get a hard copy as well. What edition is this? Oh no, this is 4th as well. So I did get a physical copy from one of the other professors, but it's 4th edition as well.
Okay.
So, yeah, well, let me know if that's a problem. We'll try to figure something out.
Okay, thank you.
Any other questions or anything? Next week, we'll be talking about unsaturated hydrocarbons. So that's carbons with double and triple bonds. And so that'll be what we'll talk about next week. And like I said, if you want to stay on till 9 and work on some problems, actually, if you don't mind, why don't we just do it right now? You have a copy of 7 right now?
Thank you. Have a good night.
Yeah,
You do, Danielle. You have a copy of the 7th edition right now.
yeah, I gotta get into it. It's on a website. I have it digitally.
Oh, nice. Yeah. So this is, and I think sometimes the chapter numbers are different. Get my reading glasses out. So 1-5. Let me know when you got it up. We'll check this.
Yeah. So this was, oops. Chapter is saturated hydrocarbons, right?
Yeah.
That's chapter 12. And this one, let me get, there's the problem.
So the 5th problem for me is what is the difference between a hydrocarbon and a hydrocarbon derivative?
Okay.
What does yours say?
Mine is indicate whether each of the following situations meets or does not meet the bonding requirement for carbon atoms.
Oh no.
Similar.
Oh no.
Yeah. 7. Formula.
Well, I wonder if I can get my hands on a 7th edition.